the only on-chain object is a multi-signature wallet. And then for the off-chain objects, we organize them into kind of actually instantiated objects which contain counterfactual state. So the advantages of having only a multi-sig on-chain, there are two advantages to this. First of all, privacy, and second of all, upgradability. So privacy, kind of the concept there is that if you have a channel with someone and you don't want the world to know that you have a channel with them, the world doesn't need to know, because the world, like other people who are not in the channel, they only see a multi-signature wallet online. So this gets you like privacy by default. And upgradability means that we try to put the least amount of code on-chain as possible. So a multi-sig is kind of very short, and a payment, like a state channel needs to contain the functionality for a multi-sig anyway. So by placing only this minimum amount of code online, we can make sure that, for example, if there's a bug found in the parts of the code that are off-chain, we can, the people in the channel can kind of agree to upgrade the code by signing new commitments, so that to kind of upgrade to a new version that fixes the bug. So those are the two advantages we get from using a multi-sig for the on-chain component. Kind of for the choice of using counterfactually instantiated objects, what we get here is we get a lot of flexibility, because we can arrange these things in whatever way we want, right? And like these are some of the examples of the things we can do in some of the specific advantages that we get from this flexibility. So the first one, localized dispute. I'm just going to go through all of them quickly. And the first one, localized dispute, means that if you have a channel with someone and you only disagree about the chess game, for example, and you have no disagreement about any of this stuff, what you can do is you can deploy this contract, and this contract, and this contract, and then the disagreement finishes, but the other things don't have to be deployed on-chain. So that's a really nice thing that you get. Locality of risk means that, for example, if this one is written by if there's a bug in this one, but there's no bug in this one, then you only lose like a small amount of money, which like, you only lose the amount of money that you have allocated to the chess game. And this is really useful, because the stuff that we have in like a conditional payment, like this can be really solid, because you only need to write one or two of them, and you can do like formal verification, bug bounties, you can stare at it really hard to make sure that it's secure. But the actual applications that people write, like we think that there's going to be a large set of applications that people write, and we can't expect all of them to be free of bugs. So if there are bugs, we want to limit the intent of these bugs. Unrestricted state deposit. So the idea here is that by organizing things into counterfactual objects, we have the property that anything that a multi-signature wallet can own can be part of a state channel. So basically, the alternative will be, for example, where your state channel supports either it supports ERC20 token, but if you wanted to support a CryptoKitty, you have to wait until the developers of the state channel kind of implement support for that into the channel. And we avoid this by making the part that controls ownership of the token off-chain. So, like for example, this one, the NPR conditional payment. So the logic in this conditional payment needs to understand how ERC20 contracts work. And it needs to know that, for example, when you read this thing and this atomic swap contract says that Bob has 5 rep, and it can read the thing, and it knows that when it wants to send out the 5 rep to Bob, what it actually needs to do is it needs to call the ERC20 contract and call the I think it's I can't remember the name of it, but it's like a specific function call that you do to the ERC20 contract. So we don't have to do the code. We don't have to. So like the users of the channel don't have to upgrade the on-chain code every time there's like a new token standard that comes out or something like that. Instant withdrawals is an answer to kind of the question just now, which is kind of that the question was, if you're in a state channel, do you always have to deploy the contract in order to end it? And the answer is no. So, like in the case of a chess game, if Kasparov and Karpov got to the end and Kasparov said, okay, I resign, like, you're right, like, I don't want to dispute this, I actually resign, you can have my money. We don't have to deploy the chess contract online, right? If they want to close the channel and if they want to kind of not interact with each other ever again, they can just do a withdrawal from the multi-sig to kind of do that, and all of this stuff doesn't need to get deployed on chain. And the last thing that we get is composability. So this is the idea that if your functionality can be split into many small pieces, you can build them in separate pieces and kind of mix and match them. So, for example, you can have an example of functionality that can be broken up is when you write a game like poker. For example, poker needs to have a concept of randomness, of like people randomly drawing a card. And when you want to do randomness between multiple parties, there's like a few different ways to do it, right? So, and it's not like a trivial thing. Like you have to think a bit about that. So maybe someone can write the code that provides a string of random numbers, and then someone else can write the code. Someone else can just reuse that code and build like a poker game on top of it. Yeah, so that's all I have in my presentation about specific to the things we do in our generalized state channels, and I kind of like talk more about